So in 1.5, we are now working with limits and continuity, and we will introduce the first of our existence theorems called IVT. So you've got the notes so that you don't have to write everything, but let's first define continuity. And so what you see on this slide is the definition of continuous. So a function's continuous at a specific point A, if and only if we have no holes, skips, jumps, gaps, asymptotes at A. So a nice rule is that we say, if I can draw the graph without actually lifting my pencil, that graph is continuous. So for all of these, we recognize that we have continuity at all 3 points, or for these examples, for every x value. So now let's define continuity using our limits. And so if a question is posed, is this graph or function continuous at a point? These 3 things have to hold. Thing 1, is f of a defined at that point? Meaning, is there an actual y value at that x equals a? If so, then we move to the next definition. So the next statement that has to be true is, does the limit exist at x equals a? And remember, that means as I'm approaching from the left, is it reaching the same height as when I'm approaching from the right? So if those 2 things hold, then I go to thing 3. And thing 3 is asking, are those 2 values the same? Are those 2 values the same? And so if the answer is yes, then we know there's continuity. Let's do an example. So if I look at this example, let's call this one example 1. If I look at that example, the first question is, does f, or if they're asking us, is this continuous at x equals 2? The first question we're asking is, does f of 2 exist? Meaning, looking at that graph, what's the y value when x is 2? And you'll notice there's that open circle, which means there is no y value. It's undefined at 2. So we can immediately say, no, there's no continuity at x equals 2 because there is no y value. F of 2 is not defined. So now let's look at this modified graph of f of x. Here, the question is, does f of 2 exist? And if I look, there it is right there. F of 2 is equal to 1. We're on a roll. Then the question is, does the limit as x approaches 2 of f of x exist? Well, let's explore. As I'm approaching from the left, and as I'm approaching from the right, it looks like that y value is trying to reach, I don't know, let's call it 3.2. So yes, that limit does in fact exist. But what do you notice? If I go to my third statement that has to be true, is that those 2 values have to be the same number. And we see that as I'm approaching, or that limit, as I'm approaching from both the left and the right of 3.2 does not equal 1. So now let's define the 3 types of discontinuity that we have. We have point discontinuity, and that's when there's just one undefined value. Just one undefined value in our graph. The next one is jump discontinuity. And you might remember, this is the one that we typically see, especially when we're working with that graph of absolute value of x over x, right? That's jump discontinuity. And that actually means that I'm starting at one specific y value and then I jump to another one to complete my graph. And the last is infinite. And this is the one where we think vertical asymptotes. There is infinite discontinuity, meaning our y values shoot up or shoot down to either positive or negative infinity. So those are the 3 types of discontinuity that we have when we're working with functions: point, jump, infinite. So here they asked us to, in this example, to verify that this function f of x is in fact continuous at x equals -3. And if I am defining continuity, the first thing is, does f of -3 exist? Does f of -3 exist? And if I look, of course it does. They tell me what it is. It's 1/8. Check. So then I go to the second one, and that is, does the limit as I'm approaching -3 of f of x exist? And that's when I now need to go to that top expression and see if it in fact has a limit. So we saw the 0/0 when we went to direct substitution. So with a problem that looks like this, we try multiplying by the complex conjugate. So that takes us right here. So we multiply top and bottom by the conjugate of that numerator. And in the numerator, that gives us a difference of 2 squares. So that took us here. And you notice in the denominator, we left it all in that factored form. Don't distribute that. Don't. So then that takes us to our next step, which is right here. And we just cleaned up the top. X plus 19 minus 16 is the same as x plus 3. And that's when we noticed, that's where my 0/0 situation was coming from. So we factor those two out, taking us right here, where we now have our modified version of that function. So we go to direct substitution. So I'm going to plug in -3 for x, which then cleans up and gives us 1/8. So let's look. So yes, the limit does exist, and it's 1/8. And what do you notice about the actual y value and the limit? They are the same. So which was to be demonstrated. QED. This is in fact continuous at x equals -3. Now let's look at this example of our piecewise graph. They're asking us for here to find the c value that would make this function g continuous. Well, the one thing I do want us to appreciate is this graph is going to be continuous for all of these values except maybe at 3, because at 3 there could be this situation where there is a jump discontinuity. So what we in fact want to do is we want to make this c value just so that those 2 points will meet at the same y value. So let's look here. So if I were to plug in 3 into that top expression, you might see I did that right there, and I plugged in 3 for x. And so 3 minus 2, that gives me 1. So I know that this graph ends at the point 3, 1. So this ends at 3, 1, which means I want this portion of my graph to begin when x is 3 at y equals 1. So if I were to plug in 3, I get here the 3 squared plus c. And what do I want that to equal? Well, I want it to equal 1. I want those two y values to meet at the same place. So then that leaves us with 9 plus c equals 1. So I want c to be -8. And I hope that is clear to you, because if I were to plug in -8 into x squared plus c, and then I plug in that value of 3, then that leaves me with 1. And look at that. Where 1 ends, the other one begins right at that point. So you'll notice for this slide that I gave some visuals in the hopes that this would make more sense. But this is just to summarize the different kinds of discontinuities and what you'll see with each. So for the first one, if we have no limit, but there is an f of x that's defined at that value, let's call that value a, then that would be an example of jump discontinuity. We would agree here that the limit doesn't exist, but there is a defined value at a. Now let's look at the second. Here we're saying the limit at a does in fact exist, but there's no y value there. There's no y value there. That would be an example of point discontinuity. And then the last one, The last one is when there's no limit that exists and there is no y value defined. And when we specify that there's no limit that exists, we could be referring to the limit being infinity or negative infinity as well. And that's what we would see with infinite discontinuity. So let's talk about how we classify these three different kinds of discontinuity. And you'll notice here that we've got point, and then we have infinite and jump. Point is referred to as removable discontinuity, whereas our infinite and our jump are referred to as non-removable. Let's walk through why that is. So here's an example right here of the graph of, or an equation for p of x. If p of x were the graph x minus 3 times x plus 1 over x minus 3, we would be able to graph that, and you would see that it looks like this graph right here. And the biggest piece is we've got that hole right there at x equals 3. And I'm hoping that you see it, because if I typed in 3, I would get this undefined value. So that would give me point discontinuity. However, what makes that different than infinite and jump is I am able to essentially fill in that hole. What the heck? That just means I can take this graph, I could make it, if I wanted, a piecewise function and say, let it be this expression for all x's that aren't 3. But for x equals 3, let the y value be 4. Let the y value when x is 3 be 4. What did we just do? We plugged the hole. And this is the only time we would be able to do that, to make this function continuous for all x's. Point discontinuity is the only one where we could plug in an ordered pair, like an x and a y, and then make that function continuous. You'll notice, though, for the, try and clear this up a little, for the remaining two graphs, if I had, I lost some of it, but if I had this graph, this red graph, q of x, well, there's nothing I could do to modify this q of x to make it continuous at that point of discontinuity. It's not like I can just add some vertical line, because q of x is supposed to be a function, right? That wouldn't pass our vertical line test. So here we'd say that's non-removable discontinuity, because pretty much there's nothing I can do about it. And the same goes for my h of x. There's nothing I could do to this green graph that would make it continuous at x equals 7. If you looked at this example, and they're asking us, find all those values where this function is discontinuous and classify them at each point of discontinuity. I'm hoping that your first go-to would be, let's factor and see what happens. And when we do that, you'll notice, boom, boom, those two terms cancel out. This is where we end up with point discontinuity, also known as removable. And so we would be able to say, when I cancel out those common factors, there is point discontinuity when my x value is negative 1/3. But wait, there's more. If I look at then this remaining piece, when x is negative 4, I'd be left with some number in the numerator and 0 in the denominator. What do we know about that? Yep, that's infinite discontinuity. And so I know that we would have infinite discontinuity when my x is negative 4. And again, we could say point discontinuity, which is removable, infinite, which is non-removable. So if we looked at this example, we would perform the same operation. We would factor to find all of our points of discontinuity. And when we did that, we would see that these two terms canceled. And when those two cancel, that leaves us with point discontinuity. So we find that there's point discontinuity when x is negative 5. And then that leaves us with that bottom term. So we've got 2x minus 5 over x minus 5. When this becomes 0, we're left with infinite discontinuity. And our infinite discontinuity would occur when x is 5. Remembering that if we were to plug in 5, we would end up with 10 minus 5 in the numerator, 0 in the denominator, and we already learned that that's going to approach one of those infinities, so we know that that gives us infinite discontinuity. Again, I would pause and just read through what the continuity over an interval means, but here are a couple of specific examples so that we can sort of identify what this means when we're talking about intervals and continuity within a given interval. So if I were starting here, looking at that graph of root x, f of x equals root x, we could say that f of x equals root x is continuous on the interval from 0 to infinity, because there is no discontinuity over that given interval. I could also say, looking at this green graph, that p of x is continuous over the interval from 1 with parentheses, because we're excluding it, to 8 with a bracket because I include it. And so this would be, or these are two examples of continuity over an interval. Now, if I look at right versus left continuity, well, I can go and reference, I could go and reference my f of x graph above for my right. So here, for example, if I'm given that a function is continuous from the right at any number a, if and only if the limit as x approaches a from the right for that function equals f of a. So case in point, this holds true. Every limit is in fact the y value for that f of x equaling root x. And then the same would hold if I had continuity coming from the left. So the last topic in 1.5 is the IVT, the intermediate value theorem. And this is one of 3 existence theorems that we're going to cover this year. So it's written here, and we'll work through just the statements that we'll always have to say when we're using it. So the first thing is, in order to use the IVT, your function has to be continuous over this closed interval. So if you've got a continuous function f over a closed interval a, b, and you've got, so now I'm going to go to this graph, you've got some y value n that falls between the y values of a and b, and those y values are never equal. Those y values are never equal. So you've got some y value n that falls in between a and b. Well, if your function is continuous over that closed interval, the IVT says that there has to be some x value c within that closed interval, a, b, such that f of c has to equal n. Let's do an example. So we have a new puppy, and the weight of that puppy is p of x. So we are referring to the weight of that puppy as p of x. So we were asked to prove that at some point in that interval, our puppy weighed 24 pounds. So let's go back and talk about the history of this puppy. So we got this puppy, and in the second week, we weighed that puppy, and he weighed 7 pounds. And then he gained some weight, lost some weight, got stressed, and then we weighed him again at week 10, and he was 32 pounds. So in order to solve this problem, the first thing we would have to state is that p of x is continuous over that closed interval. I'll say over that closed interval from 2 to 10. And I hope that makes sense to you. There's not going to be 1 week in that interval where the puppy weighs nothing and then weighs something the following week. So we know that p of x is continuous over the interval 2 to 10. We also can state what that y value is at week 2. He weighed 7 pounds. And 10th week, he weighed 32 pounds, equals 32 pounds. And since 24 falls in between pounds 7 and 32, we can then conclude by the IVT there is some weak C in, jump over the puppy, the interval 2 to 10, where the puppy weighed 24 pounds. Last one. This is on your IVT worksheet. So here I'm given a table with some measurements of the velocity of a particle moving along a straight line. We know that if we are measuring velocity, it's a continuous function, even if it's just straight zero, right? We stop. It's a continuous function. So this is asking us, what's the smallest possible number of times where v of t is exactly 4? We can go about doing this one of two ways. I can look at the table, and some of you that are more visual can actually plot this. That's going to be super useful. And maybe after we look at the table, I'll put up what the graph should look like. At any rate, we're saying over that closed interval from 0 to 14, how many times is v of t exactly 7? Well, let's look at those y values right here. We start at 3.35, and it's continuous, and then at t equals 5, it's 4.25. Would you agree with me that it must cross 4 over that interval? Yes. Now let's look from 5 to 7. It went from 4.25 down to 2.75. Must it be 4 at some point during that interval? Yes, because it started at 4.25, so it had to go back to 4 to get to the smaller ones. Moving from 7 to 9, what do you think? 2.75 to 2.55? Inconclusive. That's a maybe, but not definitively. And then the last one, what about from 2.55 to 4.7? Absolutely. So we know there are exactly 3 times, at least, where our velocity is 4 meters per second. And if we graphed this, we would see that it had to cross 4 in at least 3 places on that graph.